Okay, so yes, this is 102C, Monte Carlo methods, and welcome back to school, everybody. I don't think this is the case, but is this anybody's first quarter ever at UCLA? Okay, I don't know. Sometimes somebody might manage to slip in. I think I recognize. Looking around, I think I recognize most everybody here. I guess maybe just to verify, everyone has taken 102A, correct? Has anyone not taken 102A? Okay, well, good. And then everyone has also taken 100B. Okay, anyone not take 100B? Okay, because those are the prereqs for the class, and so the registration system should have kind of enforced that and prevented you from enrolling. But it's going to be important because ideas from, well, 100B will, some of those ideas are important, and then like most of my homework, it's going to be very code heavy. And so you want at least a little bit of coding rigor in your past. All right, so anyway, we're going to cover Monte Carlo methods, and I'm not sure how familiar you guys are with Monte Carlo methods and I don't know, the Metropolis Hastings algorithm and Gibbs sampling and things like that. But those are going to be topics that we'll cover. Those come in later on in the course. The context for Monte Carlo methods, the primary application is for Bayesian statistics. Let me try. Is that too weak now? There's no sound. No sound coming out? Okay, and I guess, all right, I guess this is it. Okay, so the primary context in which we use Monte Carlo methods is Bayesian statistics, and I'm not sure how familiar you guys are with Bayesian statistics. I know I touch on, I don't know, like the Bayes classifier and a little bit of stuff, and you guys have all seen Bayes' rule, but I don't know if you've done like straight up Bayesian statistics. And so the first week in our course will be on Bayesian ideas, and then we'll start getting into kind of Monte Carlo ideas, and we'll look at this thing called Monte Carlo integration, and then we'll look at random variable generation and all sorts of stuff. I think it's pretty neat. Towards the end of the quarter, we'll do a couple applications that I think are at least fun and interesting. I mean, my definition of fun might be different from yours, but I think it's going to be kind of neat, and so we'll do that. Okay, so we meet Monday, Wednesday, Friday right here, and then so I'm on campus during the day, Monday, Wednesday, Friday. I actually also teach night classes this quarter on Tuesdays and Thursdays, so you might be able to catch me late in the afternoon on Tuesdays and Thursdays. But generally, I'll hold my office hours from 4 to 5 on Wednesdays and Fridays, and then also by appointment. My Mondays are pretty packed, so generally probably not so available. And then, you can come by in the mornings as well on Wednesdays and Fridays. Or again, late in the afternoon, Tuesdays and Thursdays. Late, like after 4:30, 5 o'clock, somewhere around there. Okay. The textbooks that we'll use will be Doing Bayesian Data Analysis. This is the first edition. It's got puppies on the cover, and you can get it as long as you're connected to the UCLA network. You can get it for free. Okay. Same with Introduction to Monte Carlo Methods. with R. That's also via Springer link. Again, be connected to the network. You can get them for free. So I try to use textbooks that that you're already paying for through your tuition. So so that's what we have. Okay, grading. I think this is almost the same grading scheme I had for 102B if you took 102B with me in the spring. So we're gonna have homework, 30%, and then 2 midterms and a final. The midterms are 18% each. The final is gonna be 25%, and then we'll have campus wire and attendance, and then some free points thrown in there. Okay, and that should add up to 100. And so the midterms, I think I wrote them up here. It's going to be 4th week Monday, 7th week Wednesday, and then the final during our scheduled final exam time, as scheduled by the registrar. It's not something that I even have power over. Okay. Grading policies and etc. Homework. If you've taken a class with me before, and I think most of you have, the homework's going to be the same. I'm going to post an RMD file. You'll download it. You'll put in your answers, and then you'll render that and upload that back to a CCLE. And so just make sure that whatever output is requested is visible in the rendered file. Okay, we're not going to take the time to read your code or even attempt to run your code. Some of these things in the Monte Carlo methods will take a long time to run. Okay, and so we don't have the luxury of sitting there for a few minutes for each of you. It's a little scary, but I think the other door's unlocked. But, okay, anyway. Okay, and then the late penalties for the homework, 10-minute grace period, and then 5-point penalty per hour that's late. If there's some kind of situation, just upload documentation alongside your homework, and you'll be automatically granted kind of a 72-hour, 3-day extension, okay, with that, okay. Maybe I'll just go ahead and say, so going back to the beginning, regarding office hours and whatnot, if you need an immediate response for something, it's going to be best if you visit me in person, okay? I get a lot of emails, and it's hard for me to give timely responses via email. And so if you want a quick response about some situation or something, I would say visit me in person, and again, I'm on campus. I'll be on campus 5 days a week, but Wednesday and Friday, you can probably catch me in the morning, even though it's not listed as official office hours. I'll usually get to campus by around 9 a.m. or something, and you can stop by and talk to me with whatever needs to be taken care of. Okay, let me see if there's anything else. We'll take attendance via the online poll, assuming it works, and then let's see. And then we've got Campus Wire, and so sign up or log in and do that. So we've got that. As far as academic integrity, make sure you do your own work. Please don't copy someone else's homework or do that. Okay, and then I have a bunch of resources listed for any kind of student crisis situation. So I hope these issues don't crop up, but we do have resources for gender discrimination, sexual violence, and harassment, and then we also have resources for mental health and student well-being. And so please seek those resources out, if you need them. And then I think most of you who have any kind of disability, I think you are already aware of the disabilities office and that. Okay, so that's the syllabus. I don't know if there's any questions. Are we good? Okay. Is everybody a senior? And everyone's slated to graduate in come spring 2020? Who is not gonna graduate spring 2020? Okay, just one? All right, that's okay. We'll see. Are you graduating even earlier? No, okay, all right. That's fine. But everybody else, you guys are all scheduled to graduate sometime this year by 2020. That's awesome. Okay, so, and is anyone not a statistics major? All right, this is great. Okay, if everything goes according to plan, we will all see you in June at the graduation ceremony, okay? So that's exciting. All right, so you guys just have, you have to make it 3 quarters, 9 months. That's 30 weeks of instruction and 3 weeks of exams. So 33 weeks of stuff. And then you will have your degrees. Some of you will go on to graduate school. Some of you will go to work. Others of you will go explore the world, or I don't know, whatever it is you guys are doing. So that's really exciting. Okay. Well, great. And I'm excited. I hope you like this class too. It's people ask me like, what's my favorite class? And that I teach, and I don't know. Like, I like all of these classes I teach, and this one is not no exception. I really like it. It's hard for me to pick a favorite, but we do some really cool stuff here, and I especially like the fact that I don't know. I get to choose some of the, like, we have like bare minimum requirements that you have to cover in each course, and then you're given a lot of freedom outside of that. And so so I choose to kind of emphasize the Bayesian stuff a little bit here. Okay, all right. So let's just talk a little bit about what we're going to be doing. Maybe some big picture ideas. Is that visible? Okay, so for most of this class, I think our notes are going to be handwritten, and you can follow along. You don't have to take notes. You can just sit and watch as well. I'm going to save everything, post the PDFs online, and that's that. Okay, all right, so 102C, Monte Carlo methods. All right. Does anyone think they know what Monte Carlo methods are? Maybe anybody want to volunteer a definition or an idea or some concepts, or what do you think? What comes to mind when you hear of Monte Carlo methods? Or what's the Monte? Yeah. Some sort of approximation. Yeah, very good. Okay. What's the Monte Carlo part?
Some randomization.
Yes, randomization, yeah. So actually, the Monte Carlo is kind of like synonymous for gambling for Europeans, okay? This is, so like when we think gambling, we think Las Vegas, right? Maybe Atlantic City, okay, because we're in the United States. So you got, I don't know, where else are there other big gambling hubs in the U.S.? Kachanga and Morongo for Southern California. What's that?
Oh, Reno.
Reno? Okay, yeah. Okay, so Nevada, yeah. But nobody thinks of Reno. Come on. Okay. So no insult to the Amazon warehouses in Reno, but so we think Las Vegas, but if you're a European and you think of gambling, you think the Monte Carlo, okay? And okay, so anyway, Monte Carlo methods, you know, it's associated with gambling, and basically the idea is, you're doing the same thing many times, okay? Same random experiment many times. Okay, and the idea is that we might have probability questions, okay? And and you guys all took 100B, and in 100B you learned how to answer questions related to probability distributions, right? Like if you needed to find the expected value of a PDF, okay, you have you got a few ways to do it, right? You got like the method of moments, the kind of the traditional ways. You take the integral of x times p of x and stuff like that, and we try to derive or solve analytically, the questions about these distributions. Okay, with Monte Carlo methods, we use Monte Carlo methods to basically get the same kinds of answers, but for situations where the math is too hard. Let me cough. For situations where the math is too hard or complicated or just maybe not even possible. Okay, so I'll say in 100B, your math stats class. Okay, we or you learned or should have learned, how to find properties of probability distributions. Okay, so for example, the expected value is going to be the integral of x times p of x dx, or something like that. Okay, and anytime you have an integral, it can get hard, right? I'm really bad at integration, so I feel like I should retake the 30 series in math and be embarrassed. But anyway, this is what we've got, and basically we want to do similar stuff, right? Or if you want the variance of x. Do you guys remember the formula for the variance of x? It's the integral. Maybe I'll write x minus mu times p of x minus mu squared times p of x dx. Okay. Stuff like that. Okay. And in our class, basically, we want to learn the same kind of properties like mean and variance. Or, whatever else it is that we're talking about. Such as like what's the quantile for the, for this and that, okay? But maybe the math is too hard, okay? Okay. Maybe we have probability distribution that exists in like 15 dimensions, okay? And then taking the integral of this to kind of get the expected value over the 15 dimensions. Maybe this is too hard for us, okay? So we might be in a situation where the math is too hard. And so we are going to try to get an approximate answer, okay? So we try to approximate our answer using Monte Carlo methods. Okay, so like just the silliest example, okay. All right, we can say, what is the expected value of a die roll? Okay, so you go to the casino and you can play some dice games. All right, so you got this, right? And okay, what is the expected value of a die roll? Okay, so the analytic approach would be this, right? So we have our discrete distribution. So we have a PMF that looks like, I don't know how we do this. Okay, so we have X and P of X. It's 1, 2, 5, 6, and they all have probability 1/6. All right, and so the expected value is going to be the sum of X times P of X. And so this is going to be 1 times 1/6 plus 2 times 1/6 plus so on and so forth up to 6 times 1/6, right? And if we do this, we'll get 3.5, right? So this is no surprise to anybody, right? Okay, so this is this is what we get, okay, for the analytic approach, right? And so the Monte Carlo approach is much more inefficient, okay? Monte Carlo approach is very inefficient. Okay, and basically all we do is we just roll the die many, many times. Keep track of all of them and take the average. Okay, so maybe after, you know, say after 1,000 die rolls, maybe we get a mean of, I don't know, 3,542, okay? 3.542 or something like that. Okay, and this is our answer, okay? Okay, this is our Monte Carlo estimate. And that's what we get, okay? We don't get exact answers, all right? You just get estimates. You get approximations of whatever it is that we are going for. So we want to go for the expected value. We would just roll the die many, many times, take the average or something like that. Now with the advent of computers, okay, with the computer power, we can do like, you know, 1,000,000 die rolls very, very quickly and get the average, okay? Now, of course, we would never do something like this for this example because we know that the expected value of a die roll is 3.5, okay? But there's going to be other situations where the analytic approach is really hard, okay? It's going to be very difficult for us to figure out, and so we might have to use the very inefficient Monte Carlo approach, okay? So, the moral of the story is if you can do it analytically, you should, okay? Because the Monte Carlo approach is almost guaranteed to be very inefficient and time-consuming. Most Monte Carlo things you have to let run for thousands of iterations, and that's going to take time. But in certain situations, you're not sure how to do the analytic approach correctly, okay? And so, so the Monte Carlo approach, well, at least you can be fairly confident it's going to ballpark you in the correct vicinity, okay? And if you want, more accuracy, you got to run more iterations, right? And so if we can do this also, like if we wanted to do it with the computer, okay? So with R, what could I write? So I'll just write like samp is going to be what? Sample 1:6. Wait, how do I do this? Sample 1:6 size equal, let's say 10 to the 6. Replace equals true. Okay, so that will be one line, and then the next line will be mean of sample. Okay, does that kind of make sense? So we're just gonna do this, and then it'll work. Okay. There's an implicit expectation that the function sample in R is accurate and works, and it seems to be the case. Okay, seems to work. So like, let's just run this just for fun. We'll take 2 seconds. Not even take less than 2 seconds to run. It takes longer for the thing to boot up. Okay, let's see. That's not what I want. Okay, so I'm going to just write the sample that I want is sample. I'm going to sample 1 through 6. I want 1,000,000 of these things. I'm going to do sample replace as true. I'm going to ask for the mean of the sample. All right, let's just see what we get. Okay, 3.50019. Let me see. I'm going to have to make my okay, so we're getting something. Uh-oh. Oh, good. All right, I just kind of want to run this again and just see what we get. Whoops. Okay, so we're getting something very close to the real thing. All approximations. I'm waiting for one of these things to be less than 3.5, but, okay. There we go, 3.499. So, all something around the correct answer of 3.5, okay? And that's what we're just trying to go for, okay? So, so that's where we're headed, okay? There are, I guess, the Monte Carlo methods can be useful in high-dimensional settings where the math is very messy, okay? Okay, also useful in Bayesian contexts where the the PDF is hard to define. Okay, or I guess situations where the PDF is hard to define or is messy again. So this is often in Bayesian settings. Okay. And yeah, we'll see a couple applications of this. All right, so that's kind of the grand scope of the course. We're just trying to get approximations using kind of the random generation of our computers. Okay, so kind of our big goal is to get approximate answers to kind of hard problems kind of using the random generation on our computers. And so what we're going to do is we're going to start with just Bayesian concepts. We'll see if I can even get into that today. Bayesian concepts. That will be kind of our first week, and then we'll talk about random generation, maybe random variable generation. And our computer has a lot of pre-built random variable generators, right? You're all familiar with these things, R-unif and R-norm and any other distribution, R beta and R whatever, okay? So random variable generation will basically use the computer's kind of R functions, such as R norm and R unif, R binom, etc. And then we'll talk about generating our own, okay, random variables. Maybe this is a tiny bit backwards, but we'll use the computer ones first, and then we'll kind of try to make up our own versions of R norm and R unif and stuff like that. Okay, and then we'll look at what do we do in other contexts. So we'll look at kind of Markov chains. And then there's Markov chain Monte Carlo. Maybe we'll call that. We'll say Markov chain Monte Carlo, also called MCMC. Which is useful in it's more random variable generation, really, what it is. Okay, but it's useful in a lot of contexts as well. Okay, and then we'll look at high dimensional settings and some applications, and we'll look at we'll look at what's known as the metropolis Hastings, and Gibbs sampler algorithms. look at some applications. Okay, but again, this is the big goal for Monte Carlo methods is to get approximate answers to hard problems using the random generation on our computers. All right, and this is how. So a large part of this is kind of simulation. All right, when we kind of find probabilities of who's going to win the World Series and stuff like that. Okay, so the baseball season is coming to a close, and then we're going to enter playoffs and everything like that, and you have projections of who's going to win. Okay, a lot of this is done via computer simulation. Okay, which is a particular kind of Monte Carlo method. Okay. So let's see, I've got 9 minutes left, and so let's start talking Bayesian ideas, okay? And maybe before we do that, maybe we'll just have a review of maximum likelihood estimation, okay? So, okay, so how would we go about doing maximum likelihood estimation? All right, so let's say we'll use our classic pouch with, pretend that there's some mysterious marbles in here, okay? All right, so we've got some kind of pouch. All right, and then okay, there's marbles in them. Unknown quantity or whatever. I don't know, maybe it doesn't matter. Okay, there's marbles in here, and we want to know what proportion are red. Okay. Okay, and so we'll draw some, and we'll do it with replacement. Okay, so we draw marbles with replacement. Okay, and so let's say I draw 10 marbles, and 6 of them are red. Okay, right here, let's just say our exact sequence is red, red, not, red, 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 not. Okay, so let's say this is what we get. Okay, so we drew 10 marbles with replacement, and we got this sequence, and we saw a total of 6 red marbles in the bag. Okay, so okay, so we wish to estimate. What is our estimate? P hat for the proportion red. Okay, and so for maximum likelihood estimation, we would say the likelihood of our data. Okay, so P is equal to the probability of red, and then 1 minus P will be probability of not red. Okay, And I guess the PDF, I guess we'll call this F. F of x is going to be p to the x times 1 minus p to the 1 minus x, right? Okay, so that's kind of for a Bernoulli. I guess PMF. PMF is that, okay? So the likelihood of our data is going to be, the likelihood is the product of our PMFs, f of x, okay? And so we're going to end up getting p to the 6, 1 minus p to the 4. Okay, if we take the product. Okay, and then so for maximum likelihood, you know, we want to find the value of p that maximizes the likelihood. Okay, so that is to say we want to argmax, find the p, the argmax that maximizes p to the 6 times 1 minus p to the 4. And because products are difficult to deal with, the value that maximizes this thing is also going to be the argmax that maximizes the log of the whole thing as well. Okay. Okay, and so we'll take the log of that, and then we'll be done. Okay, so if we take the log of p to the 6, 1 minus p to the 4, we're going to get 6 log p plus 4 log 1 minus p, okay? And then what we want to do is we take the derivative and set it equal to 0, right? Okay, so we're going to get 6 over p plus 4 times 1 minus p times negative 1 is equal to 0. And then we get 6 over p is equal to 4 times 1 minus p, and you get 6 times 1 minus p is equal to 4p. Okay, so therefore our estimate p hat is equal to 0.6. All right, so that's not a surprise, right? So we've got, so here's our pouch, and we think, okay, so based on our data, we think p hat is equal to 0.6, right? So in maximum likelihood estimation, we find the likelihood of our thing, and then we try to maximize that thing. All right, now, okay, we're running out of time. But here's the issue, all right? If you've observed 10 marbles out of here, and 6 of them are red, do you just say, all right, well, according to maximum likelihood, p hat is 0.6. That's true. P hat, our best guess, our maximum likelihood estimate for p hat is 0.6. Okay. But does that feel, I don't know, does that feel weird at all to say something like that? Okay? What's weird about it? Yeah.
Well, one of the questions are coming in my head is we don't know how many other colors there are and how many marbles are inside the bag in the first place.
Okay, we don't know what this is. To me, the weird thing is that I'm just walking away and my answer is basically based on just 10 observations. And I'm just calling it a day there, okay? And I'm gonna say my p-hat is 0.6. I saw 10 observations. Okay, that's good enough. And let's go on. And so I guess on Monday we'll continue talking about this. But the Bayesian idea says, you know what, let's not lock ourselves in to p-hat being 0.6. Let's leave it open to some other possibilities here, okay? And so, so we'll take a look at that. We'll start exploring some kind of the Bayesian ideas a little bit more thoroughly here. Okay, looking forward to a good quarter with you guys. We'll see you on Monday.